In this video, I'll be working through Unit 1 homework problems 47 through 55. For number 47, we're given the graph of two functions, f and g, and asked to find a variety of limits. So we're going to use our properties of limits here. For part A, we want the limit as x approaches 0 of f of x plus g of x. But we know that that is equal to the limit as x approaches 0 of f of x plus the limit as x approaches 0 of g of x. Now if we go to the graph, as x approaches 0, f approaches 1. So this is equal to 1 plus, and on the graph of g of x, as x approaches 0, g approaches 0. So our limit will be 1 plus 0 or 1. Part B, we want the limit as x approaches 1 of f of x times g of x. And this is equal to the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. As x approaches 1 on the graph of f, we can see that f is approaching 2. It doesn't matter that there's an open circle there, the graph is still approaching a value of 2. So we have 2 times, and then on the graph of g, as we approach 1, as x approaches 1, g approaches 1. 2 times 1 is 2. Part C, we want the limit as x approaches 1 of f of x plus g of x. So this will be the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x. As x approaches 1, f approaches 2, so we have 2 plus, and as x approaches 1, g approaches 1. 2 plus 1 gives us a final answer of 3. Part D, the limit as x approaches 2 from the right-hand side. So I'm going to go ahead and mark this on the graph. As we're approaching 2 from the right-hand side, f is approaching 1. And on the graph of g, as we approach 2 from the right-hand side, g is approaching 3. So we want the limit as x approaches 2 from the right of 2 times f of x. Well, that's just 2 times the limit of f of x plus, and then 3 times g of x would be 3 times the limit as x approaches 2 from the right of g of x. So 2 times, and we said the limit of f as x approaches 2 from the right is 1, plus 3 times the limit of g as x approaches 2 from the right is 3. So 2 plus 9, or 11. For part E, we want x to approach 2 from the left-hand side. So let's look at our graphs. As we approach 2 from the left-hand side, f is approaching 1. And on the graph of g, as we approach 2 from the left-hand side, g is approaching 2. So the limit we want here, we can use our properties of limits to rewrite this as the limit as x approaches 2 from the left of x squared plus the limit as x approaches 2 from the left, natural log of x, times the limit as x approaches 2 from the left, g of x. Now the limit as x approaches 2 from the left of x squared, we're going to use substitution to evaluate this limit. This is not one of the graphs that we have, so we're just going to use substitution. When I substitute 2 in, I get 2 squared, or 4. And then for natural log of x, I'm also going to find this limit using substitution. When I substitute 2 in for x, I get natural log of 2 times, and for g of x, we will have to refer to our graph. So the limit as x approaches 2 from the left of g of x is equal to 2. So this is going to be 4 plus 2 times the natural log of 2, which we could also rewrite as 4 plus the natural log of 2 squared, or 4. And part F, the limit of f minus g as x approaches 2. So we can rewrite this limit as x approaches 2 of f of x minus limit as x approaches 2 g of x. Now this is a two-sided limit, so we have to check from both directions. f of x as x approaches 2, f of x approaches 1. Okay, so that limit does exist, and the limit is 1. But g of x, as we approach 2 from the left, g is approaching 2. As we approach an x value of 2 from the right, g is approaching 3. And since we're not approaching the same value from both directions, the limit does not exist. So this would just not exist. Part G, we want the limit as x approaches 3 of g of x over f of x. So using our property of limits, we can rewrite this as limit as x approaches 3 of g of x over the limit as x approaches 3 of f of x. So let's go to our graphs and see what's happening as x approaches 3. As x approaches 3, f approaches negative 2 from both directions. So that limit is going to be negative 2. For g of x, as x approaches 3, g is approaching 0 from both directions. So that limit is 0. So here we're going to have the limit of g, which is 0, divided by the limit of f, which is negative 2. 0 divided by negative 2 is 0. Part H, this is going to be the limit as x approaches 3 from the right of f of x over limit as x approaches 3 from the right of g of x. So the limit of f as x approaches 3 from the right-hand side is negative 2 over the limit of g as x approaches 3 from the right is 0. Negative 2 over 0. So this is approaching an infinite value. Our numerator is negative. Our denominator, since we're approaching 3 from the right-hand side, we can see on the graph as we're approaching from the right-hand side, those y values are negative. So I have a negative value in my numerator. I have a negative value in my denominator. Negative divided by negative is positive. So this limit is approaching infinity. I, the limit of f over g as x approaches 3. So this will be the limit as x approaches 3 of f of x over limit as x approaches 3 of g of x. So the limit of f as x approaches 3 is negative 2. The limit of g as x approaches 3 is 0. So we saw in part H that as we approach 3 from the right-hand side on g of x, we're approaching from below. So these values are actually negative. But if we approach 3 from the left-hand side, we're approaching from above. So those values would be positive. So this limit, the best we can say is does not exist. It's going to be infinity from one direction, negative infinity from the other. Part J. Now using our property of limits, we could write this as such. The square root of the limit as x approaches 1 of 1 plus the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x. All that under the square root. Which gives, so the limit of 1 as x approaches 1 is 1. The limit of f as x approaches 1, since we're approaching 1 from both sides, our limiting value is 2, plus the limit of g as we approach 1. So with function g, as we approach 1 from each side, we're approaching a y value of 1. So this is the square root of 4, which is equal to 2. And part K, we want the limit of f plus g as x approaches negative 1. So this will be the limit as x approaches negative 1 of f of x plus the limit as x approaches negative 1 of g of x. Limit of f as x approaches negative 1. Well, from the left, the limit is negative 1. From the right, the limit is negative 2. So this limit does not exist. And therefore, the sum would also not exist. Number 48, find the average rate of change of the function f over the given interval. So part A, our function is f of x equals e to the x. And our interval goes from -2 to 0. So we're going to use our average rate of change formula. We want to find f of 0 minus f of -2 over 0 minus -2. So f of 0 would be e to the power 0, or 1, minus f of -2, that's e to the power -2, over 0 minus -2, so that's just 2 in the denominator. If we want to simplify this, it's 1 minus 1 over e squared, all of that divided by 2. Or we could say 1 over 2 minus 1 over 2e squared. I just divided each term by 2. Part B, f of x equals the natural log of x, and our interval goes from 1 to 4. So our average rate of change is f of 4 minus f of 1 over 4 minus 1. F of 4 is natural log of 4, minus f of 1 is natural log of 1. Natural log of 1 is 0, over 4 minus 1. So I have natural log of 4 divided by 3. Part C, f of x equals cotangent of x on the interval from pi over 4 to 3 pi over 4. Our average rate of change on that interval will be f of 3 pi over 4 minus f of pi over 4 over 3 pi over 4 minus pi over 4. F of 3 pi over 4 is cotangent of 3 pi over 4. So 3 pi over 4 is quadrant 2. Cotangent is negative. So we have negative 1 minus cotangent of pi over 4. That's quadrant 1. So our cotangent is positive, and the cotangent of pi over 4 is 1. Over 3 pi over 4 minus 1 pi over 4 is 2 pi over 4, which reduces to pi over 2. So negative 2 divided by pi over 2. So the 2 is going to flip up. I've got negative 4 over pi. Number 49. Use the difference quotient to find the slope of y equals 2 over x at the point x equals a. Okay, we're going to take the limit as h approaches 0 of f of x plus h minus f of x over h. This is going to give us a general equation for the slope of our function. Our function is 2 over x, so the rule for this function is 2 divided by input. If I want f of x plus h, then my input is the x plus h. So this is the limit as h approaches 0 of 2 over x plus h minus just my regular function f of x, which is 2 over x, all of that over h. And now we're going to simplify this algebraically, because if I try taking the limit now, I end up dividing by 0. So substitution is not going to work. So algebraically, the way I'm going to clear out the inner fractions here is to multiply the outer fraction, top and bottom, by my LCD, which is x times x plus h, the LCD of the inner fractions. Okay, so I'm distributing like so. Okay, so that's going to give me limit as h approaches 0. When I multiply 2 over x plus h times x plus h, the x plus h's cancel out. So I have 2 times x minus, when I multiply 2 over x times x plus h, the x's cancel out. So I have 2 times x plus h all over h times x plus h. And this is equal to the limit as h approaches 0 of 2x minus 2x minus 2h over h times x plus h. I don't want to simplify the denominator because my ultimate goal is to get the h to cancel out. And this is equal to the limit as h approaches 0. Don't drop your limit. You can't drop your limit until the point where you actually substitute the 0 in for the h. So continuing to simplify here, now in the numerator I just have negative 2h. In the denominator I still have h times x plus h. So finally I'm at a point where the h's cancel out. So I have the limit as h approaches 0 of negative 2 over x times x plus h. And now I can find this limit using substitution. When I substitute 0 in for h, I get negative 2 over x times x, or x squared. So notice this is the step where I substituted the 0 in for the h, so I dropped the limit. This is my limit, negative 2 over x squared. Now we wanted to find the slope at x equals a. So all I have to do now is substitute a in for the x. So the slope of my function f of x at x equals a is negative 2 over a squared. Number 50. Y equals x squared and a equals negative 2. Part A, find the slope of the curve at x equals a. So to find the slope of our curve, we're going to take the limit of the difference quotient as h approaches 0. So the limit of f of x plus h, in this case our function is x squared, or input squared. So f of x plus h will be input squared, or x plus h squared, minus f of x is just our function, x squared, over h. So I want to find this limit. If I try substitution right now, I end up dividing by 0. So substitution does not work yet. We want to simplify this algebraically. And I'm going to do that by expanding my x plus h squared. So limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. And we can simplify this. X squared minus x squared is 0. So this becomes the limit as h approaches 0 of 2xh plus h squared over h. I'm going to continue to simplify. Remember, our goal here is to cancel out the h in the denominator so that we can find the limit using substitution. So this is equal to the limit as h approaches 0. When I factor out an h, in the numerator I'm left with 2x plus h over h. Now my h's cancel out. So this equals the limit as h approaches 0 of 2x plus h. And now that I'm at the step where I'm going to substitute the 0 in for the h, I can drop the limit from my notation. So this is going to be 2x plus 0, or just 2x. That is my slope equation. But we want this slope at an x value of negative 2. So the slope of my tangent line at x equals negative 2 is negative 4. Part B, we're going to find the equation of the tangent line at this x value, at x equals negative 2. In order to write the equation of the tangent line, we need to know the slope at the indicated point. So the slope of my tangent line is negative 4. That's what we found in part A. And I also need to know the point of tangency. Okay, so my point of tangency, I know the x-coordinate is negative 2. To find the y-coordinate, I'm going to substitute my x-coordinate into my equation. So negative 2 squared gives me a y-coordinate of 4. Once you know a point and the slope, we can write the equation in point-slope form. y minus our y coordinate equals our slope times x minus our x coordinate. Part C, we want to find the equation of the normal line at this same x value, -2. So I want the slope of the normal line, and the slope of the normal line is just the opposite reciprocal slope of the tangent line. Since the tangent has a slope of -4, the normal line has a slope of positive 1/4. And then the point of normalcy, we can call it, is going to be the same point as the point of tangent C. And we'll see when we graph it that they do pass through that same point. So again, we have a point on the line, and we have the slope of the line, so we can write the equation using point-slope form. Y minus 4 equals slope times x minus -2. Okay, so that's the equation of my normal line. For part D, we're going to sketch this. Okay, so our function is y equals x squared. Our point of tangency is at an x coordinate of -2, follow that up here, and a y coordinate of 4. So we can sketch our tangent line. We have an equation for our tangent line. Now here it might actually be helpful to write this equation in slope-intercept form just to help us graph it a little more accurately. So if I solve this equation for y, I'm going to get y equals -4x. Okay, then I distribute my -4, I get -8. I'm adding 4 to both sides. So I have -4x minus 4. So for my tangent line, it has a y-intercept at -4, and it has an x-intercept at -1. It has a slope of -4. So, oh, I missed the mark a little bit. I'm off by just a little bit there. That's my tangent line. And then for our normal line, we can also write this in slope-intercept form to help us graph it a little more accurately. This will be y equals 1/4 x. Okay, I'll distribute my 1/4 to the 2, so that gives me 1/2, and then I'm going to add the 4, so I get 4 and 1/2, or 9/2. So 4.5 is the y-intercept. So that line is coming in kind of like that. And these two lines are perpendicular to one another. So this is my normal line, and this is my tangent line. (51) Our equation, y equals 1/x minus 1. And this time our a value is 2, or we can say our x value is 2. So first we're going to find the slope of this function when x equals 2. So we're going to take the limit as h approaches 0 of f of x plus h, so 1/x plus h minus 1, minus f of x, 1/x minus 1, all over h. Okay, that's our limit. So we need to simplify this so that we can use substitution to evaluate the limit. And here I have a complex fraction. So I'm going to multiply the outer fraction by the LCD of the inner fractions. So I'm going to multiply by x plus h minus 1 times x minus 1. And that's going to give me the limit as h approaches 0. So when I distribute to that first term, the x plus h minus 1's cancel out, and I'm just left with x minus 1. Minus. And then when I distribute to the next part, the x minus 1's cancel out, and I'm left with x plus h minus 1. Over that big denominator, h times x plus h minus 1 times x minus 1. So we're continuing to simplify in the numerator, I have x minus 1 minus x minus h plus 1. And then my denominator, I will not simplify because I'm hoping for that h to cancel out. So in my numerator, I have x minus x, I have minus 1 plus 1. So continuing to simplify, now I just have minus h in the numerator, h times x plus h minus 1 times x minus 1 in my denominator. Now my h's cancel. And I have a limit as h approaches 0 of negative 1 over x plus h minus 1 times x minus 1. Now I'm ready to find this limit using substitution, so I can drop the limit from my notation. I'm substituting the 0 in for the h, and I get negative 1 over x minus 1 times x minus 1, or x minus 1 squared. So that's the general equation for my slope. I specifically want to know the slope when a equals 2, or when x equals 2. So at x equals 2, my slope is negative 1 over 2 minus 1 squared, or just negative 1. Part B, we're going to write the equation of the tangent line at x equals 2. So I know the slope of my tangent line is negative 1, and my point of tangency is 2 comma. So when the x-coordinate is 2, what's the function equal to? What's the value of my function? Well, I'm going to substitute 2 into my function. So I have 1 over 2 minus 1, or 1. I have the slope, and I have the point of tangency. So I can write my equation, y minus the y-coordinate equals slope times x minus the x-coordinate. So there's the equation of my tangent line. Part C, write the equation of the normal line. Well, the normal line just has the opposite reciprocal slope and the same point of tangency. So the point of normalcy is also 2, 1. And my equation, y minus y-coordinate equals slope times x minus x-coordinate. And there's the equation of my normal line. Part D, sketch the graph showing the tangent and normal lines. So our function is 1 over x minus 1. 1 over x minus 1. So we have a vertical asymptote here at 1. We have a horizontal asymptote at y equals 0. And then our graph looks something like this. And let's see, y-intercept is at negative 1. So we're coming in something like this. Our point of tangency is the point 2 comma 1. So we'll call that 2 comma 1 right here. So I draw my tangent line. Okay, so my tangent line is going to be approximately here. And I can simplify this if I want to get a more accurate sketch. It would be y equals, if we solve this for y, it'd be y equals negative x plus 3. And then my normal line is going to be perpendicular. So it should be here. And if we solve this for y, we can get a more accurate sketch. So we have y equals x, and then negative 2 plus 1, y equals x minus 1. So I missed the mark a little bit right there. It should be passing through that point. Okay, these two lines are perpendicular to each other. So this is my normal line. And this one is my tangent line. Number 52, y equals x squared minus 3x minus 1. And this time our a value is 0. So first we're going to find the slope of the curve when x equals 0. And to do that, we'll set up our limit as h approaches 0. F of x plus h, so it's x plus h squared minus 3 times x plus h minus 1. That's f of x plus h. Minus f of x. F of x is x squared minus 3x minus 1. All of that over h. So we have quite a bit of simplifying to do here. This is going to be the limit as h approaches 0 of x squared plus 2xh plus h squared minus 3x minus 3h minus 1 minus x squared plus 3x plus 1 all over h. So let's see what we can cancel out. We have an x squared minus x squared. We have a minus 3x plus 3x and a minus 1 plus 1, which leaves us with 2xh plus h squared minus 3h all over h. And now we can factor in h from the numerator. H times 2x plus h minus 3 over h, and where h's cancel out, and we have the limit as h approaches 0 of 2x plus h minus 3. Now I'm ready to substitute 0 in for h to find that limit, so I can drop the limit from my notation. I have 2x plus 0 minus 3. So that is my slope equation in general. I want the slope when x is 0. So if I substitute 0 in for x now, I just get negative 3. So the slope at x equals 0 is 2 times 0 minus 3, or just negative 3. Let's find the equation of the tangent line. So the slope of the tangent line is negative 3, and my point of tangency, the x-coordinate is 0, and when the x-coordinate is 0, if I go back to my original equation, substitute 0 in for x, I get negative 1 for y. So there's my point of tangency, and that means my equation of my tangent line is y minus negative 1 equals my slope times x minus 0, or just x. So there's the equation of my tangent line. To write the equation of my normal line, I need the slope of the normal line, which is the opposite reciprocal of the slope of my tangent line. My point of normalcy is same as my point of tangency. And so now my equation is y minus that y coordinate. So y minus negative 1 equals slope, 1/3, times x minus 0. I didn't really need to write the x minus 0. So y plus 1 equals 1/3 x is the equation of my normal line. Then we want to sketch the curve along with the tangent line and normal line. Okay, so we're going to sketch our curve, which looks approximately like so. Our point of tangency is 0, negative 1. So here's our point of tangency. Call that 0, negative 1. And then my tangent line, I'm just going to kind of eyeball this. Tangent line looks approximately like so. And then our normal line would be perpendicular to that, but passing through that same point of tangency. So these two lines are perpendicular to one another. Number 53. The equation for free fall at the surface of Jupiter is S equals 11.44 t squared meters, where t is measured in seconds. Assume a rock is dropped from the top of a 500-meter cliff. Find the speed of the rock at t equals 2 seconds. So we want to find how quickly that rock is moving at 2 seconds, or what is that rate of change at the instant when t is equal to 2. So we're going to find the slope. And we can do this by finding the limit as h approaches 0 of f of x plus h. So 11.44 times x plus h squared minus f of x, or 11.44 x squared, over h. So I'm going to simplify this. Now we have 11.44 times x squared plus 2xh plus h squared minus 11.44 x squared over h. Continuing to simplify, I have 11.44 x squared plus 22.88 xh plus 11.44 h squared minus 11.44 x squared, all over h. And we can cancel out the 11.44 x squared minus 11.44 x squared. And then we can factor an h from the numerator, which will cancel with the h in the denominator, leaving us with 22.88x plus 11.44h. Now we're going to find this limit using substitution. So I'm going to substitute 0 in for the h, and that's just going to give me 22.88x. So that's my general slope equation. Now I want to know the slope at the moment in time when t equals 2 seconds. So then I'm going to substitute 2 in for x. So at t equals 2, the slope of this function, which we can also call the rate of change of the function, or in the context of this problem, we can call the velocity. So just use velocity. V equals 22.88 times 2, which is 45.76, and then our units are meters per second. Number 54, at what point is the tangent to f of x equals x squared plus 4x minus 1 horizontal? If our tangent line is horizontal, well, we know a horizontal line has a slope of 0. So we want to know, when does the slope of this function equal 0? Let's get a general equation for the slope and set it equal to 0. So to get the equation for our slope, we're going to take the limit as h approaches 0 of our difference quotient, so f of x plus h be x plus h squared plus 4 times x plus h minus 1, that's f of x plus h, minus f of x, so x squared plus 4x minus 1, all over h. And we're going to work on simplifying this until we can cancel the h out from the top and bottom. So x squared plus 2xh plus h squared plus 4x plus 4h minus 1 minus x squared minus 4x plus 1. All of that over h. And we can cancel out x squared and what else? 4x and this 1. So this gives us the limit as h approaches 0. In the numerator, we are left with 2xh plus h squared plus 4h all over h. So we can factor an h out from the numerator. Okay, h's cancel out. Then we have the limit as h approaches 0 of 2x plus h plus 4. Now I'm ready to find the limit using substitution, so I can drop the limit from my notation. Letting h equals 0, I get 2x plus 4. So that's the general equation for my slope, and I want to know, when does that slope equal 0? If the slope is equal to 0, my tangent line is going to be horizontal. So we just solve for x here. We subtract 4 on both sides and then divide by 2 on both sides, and we get x equals -2. Now the question said, at what point is the tangent line horizontal? So we want to give the x and y coordinate. So my point will have an x coordinate of -2, and to get the y coordinate, I'm going to substitute -2 into the original equation. So -2 squared is 4, plus 4 times -2, that's -4 minus 1, -5. And our last question, number 55. A bungee jumper dives from a tower at time t equals 0. Her height s in feet at time t seconds is given by the following equation. S of t equals 100 cosine of 0.75 t times e to the negative 0.2 t plus 100. So make sure that if we're using our calculator here that you are in radian mode. This is the cosine of 0.75 t that is measured in radians. Part A, write an expression for the average velocity of the bungee jumper on the interval from 1 to 1 plus h. So the average velocity on the interval from 1 to 1 plus h. Our average velocity formula, we want s of 1 plus h minus s of 1 over 1 plus h minus 1. S of 1 plus h minus s of 1 over 1 plus h minus 1. So s of 1 plus h, we're going to substitute 1 plus h in for t in our equation. So 100 cosine of 0.75 times 1 plus h times e to the negative 0.2 times 1 plus h plus 100. All of that is just s of 1 plus h. Then we're going to subtract s of 1. S of 1, I'm going to go to my calculator, and I'm getting approximately 159.906 for s of 1. So all of that over h. We can simplify that a little bit. We can add the 100 to the negative 159.906. And so our expression for average velocity on this interval is going to be 100 cosine of 0.75 times 1 plus h times e to the negative 0.2 times 1 plus h minus 59.906 all over h. For part B, we're asked to use technology to estimate the value of this limit as h approaches 0. Substitution isn't going to work because substitution would cause me to divide by 0 here. So using my calculator, I'm just going to input a number that's close to 0. Let's try 0.0001. Okay, if h is 0.0001, then this becomes 100 times the cosine of 0.75 times 1.0001 times e to the negative 0.2 times 1.0001 minus 59.906 all divided by 0.0001. And that is giving me approximately negative 57.659. And the units on that, our change in distance over our change in time, is going to be feet per second. Part C, what is the meaning of the value of the limit from part B? What are the units? So we talked about the units, and this is going to be her average velocity, or it's an approximation. Well, our calculation in part B was the average velocity from time t equals 1 second to t equals 1.0001 second. That's such a tiny time interval that what we're really doing is approximating her instantaneous velocity. So that is approximately her instantaneous velocity at time t equals 1 second.